Welcome to the deep dive. In the world of AI, it often feels like the mantra has been go big or go home. These larger models, they tend to pack more punch, more accuracy.
Yeah, absolutely. But that massive power,
Yeah,
well, it guzzles energy, doesn't it?
yeah,
And needs some serious computing muscle behind it.
exactly. And while, these huge models are incredibly impressive, what they can do, their size creates these very real practical hurdles.
For sure. Think about just access, right? Not everyone's got a supercomputer handy. And then there's the whole environmental footprint concern, which is definitely growing.
Right. And that's really why there's this growing excitement around smaller, maybe more nimble AI models. We're starting to see some pretty interesting examples pop up.
Like that one from AI2, the Allen Institute.
Yeah, exactly. Their 1 billion parameter model, apparently it's holding its own, even beating some much bigger models from the tech giants in certain
And
tasks.
Microsoft's 5.4 too, right?
Yeah.
The reasoning one.
5.4 reasoning plus. Yeah, only 13 billion parameters,
Mhm.
but showing real smarts in things like logic, math, science problems.
Mhm.
It kind of makes you wonder if we always need those absolute behemoths.
It really does. These things suggest a really interesting shift, I think. A move towards, let's say, smart efficiency. Finding that sweet spot between capability and practicality.
And that right there brings us to what we're really digging into today. We've stumbled across some intriguing details about a new approach from DeepMind.
Ah, DeepMind. Always up to something interesting.
Seems like it. They've recently filed a patent application, and it looks like it's tackling this exact challenge, trying to capture that large model magic, but in, a more energy-sipping package.
Okay, so bridging the gap.
That's the idea. So our mission today is to unpack this patent, try to figure out what DeepMind's really up to, and, what it could mean for the future of AI. For you listening, think of this as your shortcut to understanding a potentially game-changing bit of tech.
All right, let's dive in.
Okay, so what's the fundamental problem they're trying to solve here?
Well, what's fascinating is the core question DeepMind seems to be wrestling with. Imagine you've got this really powerful AI, it's already trained, works great. The question is, how do you figure out the absolute minimum amount of training data you need
Okay.
to teach a smaller AI to perform just as well?
Ah, I see. So it's not just about shrinking it, but shrinking it smartly.
Exactly.
Yeah.
Think of it like you've perfected a recipe for this massive banquet, feeds hundreds. Now, how do you scale that down precisely for a small dinner party, maybe just 6 people, without losing any of the flavor or the quality?
That's a great analogy because you don't want to just randomly cut ingredients, right? You need the right proportions.
Precisely. It's about shrinking it intelligently so it doesn't lose its smarts.
Yeah.
And this patent, it seems to really hinge on understanding that relationship between a model's size and the data it consumes during training.
Okay, so there's a specific system they're proposing.
Yes, their patented system. They describe it as determining training data sizes for training smaller neural networks using shrinking estimates. That's the formal bit.
Right.
But the central idea they introduced, the catchy part, is something they call model shrinking mapping.
Model shrinking mapping. Okay, that definitely sounds like the secret sauce. What does that actually mean? Can you break that down a bit?
Well, think about when you resize a photo on your computer. There's a clear ratio, right, between the original size and the new size.
Sure.
Model shrinking mapping is, it's kind of like that, but for AI models. It's essentially a way, like a ratio equation,
Yeah.
to compare a larger, successful AI and the huge amount of data it learned from to estimate exactly how much data a smaller AI would need to reach a similar level of performance.
Oh, it's like a smart scaling tool for AI recipes.
That's a really good way to put it.
Hmm.
It takes the ingredients of the big AI, its size, its training data, and calculates the ideal ingredients for a smaller but equally capable version.
Okay, that makes sense.
And the real power here, the benefit they're aiming for, is that it helps developers figure out precisely how much data that smaller model needs.
Ah, so you don't waste resources.
Exactly. You avoid overtraining it, feeding it too much data, which wastes time and compute power, or conversely, underfeeding it, which means it won't reach its full potential.
Right, you want that Goldilocks amount of data, the perfect learning diet for the little AI.
That's the goal.
Mhm.
And DeepMind spells this out pretty clearly in their filing. They say, and I'm quoting loosely here, that the second smaller model will achieve substantially the same performance as the first machine learning model,
Okay, substantially the same.
despite having lower computational cost, less latency, and a small environmental impact at inference time.
Wow. Okay, that phrase, substantially the same performance, despite all those advantages of being smaller, lower cost, less latency, better for the environment. That's the real kicker, isn't it?
Absolutely. That's the potential game changer right there, getting that near top-tier AI performance, but with just a fraction of the resources.
And that hits on that desire for aha moments, right? The idea you could get this high-level performance without needing, a power plant next door.
Exactly. Imagine deploying really powerful AI on devices where it just wasn't feasible before because of those resource limits.
Okay, I'm definitely intrigued. So where does this model shrinking mapping idea actually come from? Is there more detail in the patent itself?
Yeah, let's dig into the specifics a bit. We're looking at the European patent application. The number is 232.06829.6, filed back on October 30th, 2023.
Okay, pretty recent then.
Very recent. And they've also filed a U.S. application claiming its benefit, which just underlines that this is, cutting-edge stuff they're working on.
So what's the core idea presented there?
The central goal described is training this smaller machine learning model so that it essentially performs as well as a larger model. They even refer to that larger one potentially being compute optimal.
Compute optimal. Okay, what does that mean exactly? Like the perfect balance?
Yeah, think of it as the Goldilocks point for training that specific large model, where the model size and the training data were perfectly balanced for the computing power they used to train it. The most efficient way to get that result at that scale.
Got it. So how does the process actually work according to the patent?
Okay, so it lays out a few steps.
Hmm.
First, you need the details of the bigger model, specifically its size.
Which usually means the parameters, right?
Right, typically the number of trainable parameters, those internal knobs the AI adjusts while learning. And you also need to know how much training data it used to reach its target performance level.
Okay, size and data of the big one. Check.
Then you specify the target size for the new, smaller model you want to train.
Makes sense. You know where you're starting from and where you want to end up size-wise.
Exactly. And then the model shrinking mapping comes into play. It uses specific parameters, essentially a formula, to calculate the required amount of training data for that smaller model. This calculation is based heavily on that ratio, the relationship between the larger model size and the intended smaller size.
So it's heavily mathematical based on comparing those parameter counts. Like if the small one has half the parameters, the mapping tells you if it needs, say, double the data or maybe 4 times or something else entirely.
That's the core principle, yes. It provides a quantitative estimate based on that size ratio. And just to reiterate, when they say model size, it almost always refers to that number of trainable parameters in the neural network.
Okay. And you mentioned compute budget earlier, FLOPs.
Right. We should touch on the training compute budget. That's basically the total amount of computational effort measured in FLOPs, floating point operations per second, that goes into the training process. It's like the total energy bill or the total work done to teach the AI.
Got it. So this mapping helps optimize the data needed for a smaller model, likely reducing the compute needed later during inference, even if the initial large model was compute optimal for its size.
Precisely. And thinking about real-world benefits, where could we actually use this?
Yeah, what are the applications?
Well, a key one they highlight is adapting these powerful, often huge AI models so they can actually run effectively on devices with limited resources.
Like phones or wearables.
Exactly. Your smartphone, your smartwatch. They have way less memory, way less processing power than the massive server farms where these big models usually live. This model shrinking mapping could let developers create smaller, efficient versions of really sophisticated AI.
That could run directly on my phone.
Potentially, yes. Delivering similar performance for certain tasks, but locally, without needing that constant cloud connection, and crucially, without killing your battery life.
Wow, that really would be a game changer for mobile AI. Imagine having genuinely smart assistants or features running right there in your pocket, offline even.
That's the potential. The patent also mentions something interesting. You might actually need to generate more training data for the smaller model to reach that target performance.
Wait, more data for the smaller model? How does that work?
It sounds counterintuitive, right? But the idea is that the smaller model might need more examples to learn the same underlying patterns as the larger one, which has more internal capacity. This extra data could just be making more copies of the existing data. Or it could even involve using other AI models to generate new synthetic data specifically tailored to help the smaller model learn more efficiently.
Huh. So you shrink the model size, but you might actually increase the dataset size in a targeted way.
It's a possibility the patent accounts for. The mapping helps determine how much data, potentially more, And the crucial point, the ultimate goal, is for this smaller model to be trained to optimize the same objective, perform the same task as the larger one, just using a potentially different, maybe larger data set guided by this mapping.
Okay, so same smarts, smaller package, possibly a different, maybe bigger learning diet prescribed by this mapping. Now, this whole idea, finding the right balance between model size and data, it feels familiar. Doesn't it connect to other concepts in AI?
Oh, absolutely. You're probably thinking about scaling laws. Remember Chinchilla?
Vaguely. DeepMind again, right?
Oh,
About finding the best mix for massive models.
exactly. The Chinchilla scaling laws, which DeepMind introduced a couple of years back, were all about figuring out that optimal relationship between model size and training data when you're aiming to build the very largest, most powerful models possible, given a certain fixed compute budget.
Right, optimizing for the giants.
Precisely. And what this new patent seems to offer is a way to kind of leverage the wisdom gained from training those giants, the insights from those scaling laws, and apply them intelligently to training smaller, more efficient models.
Ah, okay. So it's like saying, we figured out the physics for building a Saturn V rocket. Now let's use some related principles, maybe this new mapping, to design a really efficient, high-performance electric car.
That's a fantastic analogy.
Yeah.
It could potentially let developers bypass the need for those absolutely massive compute resources every single time they want to create a capable but more practical, smaller AI model.
Like a shortcut to efficiency built on the shoulders of giants, so to speak.
Kind of, yeah. And the advantages aren't just about saving compute costs during training or inference, are they?
No, you mentioned latency earlier.
Right. Reduced latency is huge. Smaller models generally respond faster. Think about real-time translation or controlling a robot or autonomous driving systems. Speed matters.
Definitely. Milliseconds can make a difference there.
And as we touched on, the lower energy consumption during inference when the AI is actually doing its job out in the world, that has really significant positive implications for the environment, especially as AI becomes more pervasive.
That environmental point feels increasingly important. And thinking practically, this also sounds like a potential big win for businesses, doesn't it? Especially smaller ones.
For sure. It could make powerful AI solutions much more affordable and accessible. You might not need that colossal tech infrastructure to get sophisticated AI capabilities.
So it could sort of democratize high-performance AI.
That's a strong possibility, yes.
Yeah.
Opening the door for a much wider range of applications and different kinds of organizations to leverage AI effectively.
Okay, so let's try and wrap this up. To bring it all together, what's the absolute key takeaway here? What should we, and you listening, really hold on to from this deep dive into DeepMind's approach?
I think the core message is this. DeepMind seems to have developed, or is developing, a really clever method, this model shrinking mapping, specifically designed to figure out the right amount of training data for smaller AI models
Okay.
so that they can perform pretty much on par with their much larger resource-hungry predecessors.
Mhm.
It offers a potentially clear path towards AI that's not just powerful, but also way more efficient and ultimately more accessible.
That definitely feels like a significant potential shift. More efficient, more accessible, but still powerful AI.
Okay, great summary. And on that note, here's maybe something provocative for you to mull over.
Oh. How could this model shrinking mapping, if it really pans out, reshape the whole landscape? Not just AI development, but how we actually use AI day to day. Could this finally be the key that unlocks genuinely powerful AI on all sorts of everyday devices, from your toaster to your car, and maybe drastically cut down AI's carbon footprint in the process? What completely new things might suddenly become possible with these smaller, smarter models? It's certainly fascinating to think about. Thanks for taking this deep dive.